I am Soya Eguchi from 4D Fabrication Lab at Keio University. I will talk about pneumatic auxetics, inverse design and 3D printing of auxetic pattern for pneumatic morphing. I propose a method of transforming to the expected shape by removing air. I also propose the generation of 3D printable skeleton data for the transformations. In the research area of origami and kirigami, several inverse designs from target geometries have been done. However, most of them are designed without using thickness information because they assume thin materials such as paper. I redesigned the algorithm based on the kirigami simulator to take account of thickness. This allows for transformation by removing air. In this study, as an initial experiment, various skeletons were placed in a membrane to remove air and check their behavior. In this context, I saw that the Auxetic pattern could change its shape by controlling the size of the triangles. However, the model that simply extruded the 2D simulation results did not transform or produce only small transformation. Therefore, we needed to simulate a 3D geometry with thickness in kirigami. This is our simulator. From the input surface, the size of triangles is varied according to the size of the undulations. This is done for two shells, one on the outside and one offset on the inside, and then rotated and connected to create a skeleton. The figure shows the behavior of the 3D printed skeleton when placed in a membrane and deflated. It is gradually deformed by removing air. At this time, the hardness of the shell also gradually becomes stronger. The algorithm can be adapted to different shapes. As applications, we produce knee supporters and sunshades. The knee supporter is made to fit snugly, using data from scans of the patient's feet. Changing the air pressure also changes the stiffness of the supporter. The sunshade is made with a focus on reducing the size of the gaps when air is removed. Air can be added or removed from the membrane to create multi-step transformation. As a conclusion and future works, we should investigate the behavior when the size is varied. Furthermore, pneumatic auxetics has the potential to be further developed in combination with other technologies. For example, it would be possible to make a structure that interacts with the surrounding environment by sensing the weather or temperature and automatically actuating structural morphing. Thank you.